It's a pleasure for me to introduce the first speaker of today, Jacopo Zanchettin from CISA, which will talk about Galois objects of algebras. As always, each speaker will be happy to answer your question at the end of his talk, so if you have any, please raise your hand and we will give you the floor. So please, Jacopo, the stage is yours.
So mic off. Okay. So anyone can see the screen, I think. And first, I want to thank the organizers for this nice initiative. It's very appreciated in these times of isolation for everyone. So today, my talk is in the big field of non-commutative geometry, which essentially is the field of mathematics and mathematical physics, where the objects between topology, geometry, and algebra are studied. You may know, like some results has the Gelfand duality between topological spaces and sister algebras, or the Serre-Swan theorem between vector bundles and modules over commutative algebras. Today, my focus is on principal bundle, so principal bundle and Hopf algebras. And the goal of this talk is to show that what in the classical case, so in the topological case, is a very trivial and boring example, so a bundle over just a space made out of a point. In the non-commutative world is more interesting, is way more interesting. So the talk is divided in 3 parts. And the first 2, I will just introduce and define our main tools. And the last one, I will show, well, the main result. Okay, so we start by recall what a fiber bundle is. Well, a fiber bundle, roughly speaking, is just a space. It can be a topological space, a smooth manifold, whatever you want, but that locally looks like a product of 2 spaces. So more precisely, topological bundle in this case is a datum of free object, a space X, a space B, and the continuous map pi subjected to this relation. So pi is a surjection and continuous for every point in B, which will be called the base space. The pre-image is homomorphic to the typical fiber F, and for any open in the base space U, we have an homomorphism from the pre-image of this U into the direct product of U times F. And this is the formalization of the sentence above, so that locally is just a product. Of course, there is more about fiber bundle, but for our purpose, this definition is enough. So as I said, F is a typical fiber, X the total space, B will be called the base space, and pi the projection. Okay, the first example of a bundle is just the direct product, or the Cartesian product if you want, of 2 spaces, B and F, in this case topological spaces. And if we take the map pi to be the projection onto the first factor, okay, we have that the triple X by B is a fiber bundle, and we call this bundle the product bundle. Okay, so now that we have bundle, we have we can define morphisms of bundle. So in this way, we'll have a good, nice category. So the arrows in this category are bundle morphism, which are nothing more, nothing less than 2 maps, in this case, continuous map from the bases B and B prime, and the total spaces X and X prime, making this diagram commutative, meaning that, of course, the composition of these 2 maps equals the composition of these 2 maps. We say that 2 bundles are isomorphic when the pair F phi is made out of homeomorphisms. So we can identify the total space and the base space. A bundle which is isomorphic to a product bundle is said to be a trivial bundle. And we mostly are dealing with trivial bundle in the present talk. So, okay, now a not very interesting result, but it is necessary for our talk, is that if we take the simplest possible space as a base space, so a base made out of just a point B, any fiber bundle over this space is trivial by definition. You can see this by just looking at the definition. Here we have only one chart U, and so the product is, well, the bundle is homeomorphic to the product of B and F globally, not just locally. So any bundle over a single point is trivial. Okay, but we want to start, well, I want to study not just fiber bundle, but a particular type, a particular category of bundle, a subcategory. So the category of principal bundle. So there are very different type of definition one can introduce for principal bundle. The one I'm gonna use is the following. So consider a space X, a topological space, and a topological group G, and a G action on the right of X. So we are given with a map from the product X times G into G in the following way. And we are asking that this map is continuous. We can define another topological space B, which is the space of orbits of this action, and taking the canonical projection that takes a point X into its orbit. And moreover, we are given with a map, which is denoted by alpha from the product X G into X times X, which is the following, okay? And this map is injective, so yes, it's injective if and only if the action of G on X is free, which is, okay, a very trivial observation if you look at the definition of alpha. And the image of this map is exactly the fiber product, which is the space made out of pairs XY, such that the projection of X equals the projection of Y. Okay. So this construction is our definition of a principal G bundle. Okay, so as a triple X pi B, where X is a G space with a 3 action of G, and B is the space of orbits, and pi is the canonical projection. Okay, if we look back at the definition of fiber bundle, a fiber bundle here for this bundle, the fiber F is identified with this space, with the group G. Okay, and well, maybe a more, say, natural or maybe common definition of principal G bundle is a bundle where a total space is a G space, and the action of the group is such that is free and transitive on fibers. But if you take a look to this map alpha, well, you have that the action of G is transitive and free on fibers. Okay, so the two definitions are equivalent, fortunately. Okay, now our goal, no, well, I want to say a little more on the morphisms in this category. So a morphism of principal G bundle is a pair of maps that form a bundle morphism as before, but in addition, we ask that the map of the total spaces preserves the G action, okay? And again, so if the pair is made out of homomorphisms, we are given with an isomorphism of principal G bundle. As before, the product B times G is naturally a principal G bundle and is the product bundle or the trivial G bundle. And any other bundle yeah, isomorphically, this bundle here is just the trivial, called the trivial bundle. And again, if we take the base space, the simplest one, just a point, we have that any principal G bundle is trivial omit. So most importantly, in this setting, the isomorphism classes of principal G bundle over a singleton contains just one element. So if you want it, again, it's a singleton. Okay, nice. So far, so good, I hope. Okay, now we want to pass to the algebraic world. So we want to see what this bundle structure given G, pi, and X, B, whatever, how this structure induces an algebraic structure. And for simplicity, we assume for now that G and X are just a finite group acting on a finite set. So we can consider the vector space of functions over G and X valued in the complex numbers. And with pointwise multiplication and product, these two spaces becomes algebras, particular commutative algebras. And for G, since we have the G structure, so the group structure, we can define another two maps, namely the map that takes an element in OG, so a function that takes a point in G and maps it into the complex numbers, into the tensor product in the following way. So delta of U acts on the tensor product GH, evaluating U in the product GH. So this map is induced by the product in G. And the existence of an identity in G gives this map from OG into C. And by taking U into evaluating U at the identity. And here we are using, well, to be precise, since the product is a map from two copies of G into G, here the map delta is actually a map from OG into O of G times G. But here we are using that OG times G equals the tensor product of these two algebras, which is a result that holds for, in particular for finite groups. And so we are given with this map in this way. It is easy to see that both maps are algebra homomorphisms, so preserve the algebra structure, and we will call them respectively the coproduct and the co-unit. Moreover, we are given with two equations, which are a restatement of one, the associativity of the product in G. Okay, so if we take this combination of maps into the algebra OG, these two are equals, meaning that if we evaluate U, well, this map applied to U gives a map on the which, how to say, okay, which argument is given by three element, the tensor product of three element in the group. And this statement tells that just that U of G times H times L, another element, is well defined despite, well, is independent of the order of the product. So it's just the associativity in the group. Okay, nothing so difficult. And the other equality is just the existence of the identity, so that if we evaluate U into G times E, this is actually the same as evaluating U in G. But since this is a group, we have also the inverse. So we have a third map, which is induced by this group structure on this algebra, and is the following. So S of U is an endomorphism, and takes just an element G into its inverse, and then we take the evaluation with the function. And this map is called the antipode. And I will tell you later what this structure on OG is, because it's a well-known structure. But here I'm following a sort of a bottom-up approach. So we are starting from a very particular example. So, and then I will give you the general definition of all the structures. Maybe it will be more clear. I don't know. Okay, so now that we saw that having X and G, we have two algebras, and on G we have more structures. Now we are asking what the action of a group G to H, sorry, not to H, to an action on X induces algebraically. So the action of G on X gives this map from the algebra of function over X to the tensor product, where H is the algebra over G, and is just given by the action we wrote before. Okay, the property of the map delta is the following, and explicitly we have that this means that if we take the product in the group and then act on the space, is the same as act before on the space with G and then with H. And this identity here, okay, is just tells us that well, acting with the identity is leaves an element X unchanged. And okay, so again, we'll see what this algebraic structure is. Okay, so for this map, we can define the subspace of elements for which this action is trivial, and is the following set, which is denoted by A co H. And okay, one can prove that this is actually a subalgebra of A, and nothing more. Okay, in the particular case of an action, so in our case of an action of a group G on the space X, we have that this A co H is identified with the functions over the space of orbits, because if we recall the definition of delta, we have that F equals is an element in A co H if and only if it's constant over equivalence classes. Okay, and so finally, if we consider a principal G bundle, so X is a G space free with the free action, the projection pi, and the space of orbit B, the canonical map alpha, the bijection we wrote before, induces a linear map, which is a linear isomorphism from the tensor product, this time not on C, not on the ground field C, but on the algebra of coinvariance, so this algebra here, into the tensor product A tensor H. And the map is given by this combination here. Okay. So at this point, we have seen that having a principal G bundle, we have a lot of algebraic structure. So we can give, yes, a lot of to the algebraic world. And okay, so now we define what kind of, well, we just give a name to all the structure we introduced. And so we start with the Hopf algebra. So just, well, Hopf algebra is, for us, is an algebra over the field of complex numbers, H, together with three linear maps, delta, epsilon, and S, where the first two are algebra homomorphisms, and S is an algebra anti-homomorphism, meaning that reverses the order of products, such that we have this equality here that we call co-associativity, and it is, in the case of the algebra of the group, is that just the associativity of the group, and this identity is called the co-unital property of Hopf algebra. And well, okay, for this S, if we denote delta as this finite sum, well, not finite, just this sum, the property that defines an antipode, beside being an anti-homomorphism, is the following, okay, which is more complicated. It is related with the dual of the algebra, but I'm not want to talk to this because it may confuse you, and we are not gonna need this. So Hopf algebra is the datum of an algebra with these three maps. So we can conclude that the algebra of function over a group G is a Hopf algebra, okay? And well, I said before that group was taken to be commutative, but actually we can allow to be a bigger class of groups, like if you want algebraic group, which are more interesting in applications. And okay, just observe that if the G is abelian, then we have that OG is co-commutative, and the co-commutativity is written here. Then okay, that this coproduct is the same if taking the first tensor, the second, and the other way around. Okay. As an example of another example of Hopf algebra, and again, given a group G, we can consider the group algebra, which has a set is linear, the set of linear combination of element of these four, where lambda G are complex numbers and are non-zero just for finitely many elements in G. And okay, is a vector space for which the basis is just all the elements in G, and the product is the following. All the stuff I think is known for most of you. And it is an Hopf algebra if we define these three maps here and extend them linearly. Okay. Yes, so this is a nice example of Hopf algebra, and we're gonna use this later on. Okay, so now the group action on a space, we saw that induces some sort of an algebraic structure over OX, and that structure is actually a comodule algebra structure. So given an Hopf algebra H and an algebra A, both taken to be unital, A is a comodule algebra over the Hopf algebra H if there is an algebra homomorphism from A into A tensor H, such that we have the previous equality, the previous equations. Okay, so this tells that, okay, if it acts before in the algebra, so if we take the coproduct and then acts with the, well, the stuff I said before is one of those cases that the equation is better than the words. So just look at the equation and everything is, I think it's kind of fine. Okay, so as I said, then the action on a space X of a group G gives a comodule structure over the algebra OX. Okay, and if we take back our Hopf algebra CG, the group algebra, there is this nice result that tells that any CG comodule algebra is a G-graded algebra and the other way around, where G-graded algebra is an algebra which have a linear decomposition, has a direct sum over the group G into linear spaces AG, such that we have that the product of two components satisfies this equation, and the identity lies in the component related to the identity in the group. So here the identity in the algebra, here E the identity in the group. And as I said, any G-graded algebra is a comodule algebra, by defining this co-module structure, so this co-action here, and extend by linearity over C. And also the converse is true. So again, I repeat, any co-module algebra over C of G is a G-graded algebra. Okay, finally, we have now the definition of the algebraic structure defined by a principal G bundle. So if we consider A to be an H co-module algebra and B a subspace of A is said to be a Hopf-Galois extension of B if B is the subalgebra invariant under the co-action on A. And moreover, the canonical map beta given by this formula here, canonical because it depends only on the algebra structure on A and the co-module structure on A, is a bijection. Here, the tensor product over B is just the quotient of the normal tensor product. So it's just tensor product, well, the normal tensor product where the two elements AB tensor A prime is identified with the element A tensor B A prime. Okay, so we have that a principal G bundle. If we take then OX to be A, B to be O over the function over the space of orbits, we have that A is a Hopf-Galois extension of this algebra of co-invariance element. Okay, and in a sense, since, okay, here I'm, okay, well, I'm gonna say something later, okay. So for the case of a principal G bundle, if we go into the algebra setting, so if we write down the Hopf-Galois extension given by function over X, these algebras, the algebras involved are only commutative algebras, okay? And okay, so now if we consider Hopf-Galois extension for which the algebra A may not be commutative, we define it as a non-commutative principal bundle. Okay, here there is a bit of hand waving, but the point is that once you're given with a commutative algebra, there is a way to reconstruct the space, a space X for which OX is the algebra you started with. So we are relying, we're sitting on a one-to-one correspondence when the algebras are commutative. Okay. So by dropping the commutativity, we are imagining them, so these algebras, to be the algebras of function over some non-commutative spaces. This is basically what I said at the very beginning, and what is and non-commutative geometry is this stuff at the end of the day. Okay, so I'm about to finish. So the last couple of slides are about, okay, so our example, so the group algebra of a group G is a Hopf-Galois extension if where the co-invariants are the subalgebra related to the identity in the group, if and only if it is strongly graded. And that means that if we take an element in the component AG with an element in the component AH, and you take the product, this product is an element in the component AGH. This for every element in the group G. And yes, this, and so in a sense, this kind of so strongly G-graded algebra are possibly, yeah, are Hopf-Galois extensions or non-commutative principal bundles. Non-commutative when A, of course, is non-commutative. Okay, to finish, more or less, I want to say that As in the case of bundles, there is the definition of trivial bundle. Also, in the case of Hopf-Galois extension, there is definition of a trivial Hopf-Galois extension, and it's just the one you may expect is just taking the tensor product of B with the Hopf algebra H, and everything is, well, canonically defined, and is not that difficult to write down, but it's very long, so I will just skip it. This is to say that there is a notion of triviality also for Hopf-Galois extension. And okay, yes. Now, as we said before, in the classical case, so if you want a commutative case, if you consider a principal G bundle over a singleton, the isomorphism classes of those bundles is just made out of one element, the trivial bundle. What happens in the non-commutative world is something more surprising than I tell you in 1 minute. But before, just a bit of a reasoning. Okay, so if we take a look to the algebraic counterpart of a bundle for which the base space is just a point, it's easy to see that the algebra of function over a singleton is just the field C, okay, because that space is the function, which are a complex number if evaluated in B, and so okay, I think it's kind of clear that it's just C. Or if you want to be more precise, you use characters of these algebra, but well, they are not needed. Okay, so for this reason, we define Hopf-Galois extension for which the co-invariant subalgebra A, or A co-H or B, is the ground field C. So in a sense, in our sense, Hopf-Galois extension such that B equals C are just non-commutative principal bundle for which the base space is just a point. Okay. And yes, this is the sentence I said 3 seconds ago. Okay, last 2 slides. The remarkable difference in this non-commutative setting is that the isomorphism classes of Galois object for a Hopf algebra H can be highly non-trivial, so that we can have an infinite number of equivalent Galois object for a given Hopf algebra. And yes, as we said, as we saw before, if we take the Hopf algebra, the Hopf algebra called the group algebra, so C of G, we said that strongly graded G algebras are the Hopf-Galois extension of the component of the identity. And when it happens that this component is the ground field C, then we have that A is a Galois object. And the last result, which is well, actually, there are no, the point is, well, in a classical case, you have that, well, the classification of isomorphism classes over a singleton is the most trivial thing you have in the principal bundle setting. But in this setting, there are a lot of results about isomorphism classes of Galois object for a given Hopf algebra. But for the group algebra, there is this very nice result, which tells that there is a one-to-one correspondence between isomorphism classes of Hopf algebras, of Galois object, of the group algebra, of the group G, with the second cohomology group of the group with coefficient in the non-zero complex numbers. Okay, and so this tells, for instance, that if we take the direct product of R copies of a cyclic group of order n, there is this result, which is a group with the proper, with its exponent. And so the important thing that this is non-trivial. Okay, so is as exactly what I said at the beginning. So we are considering the most trivial example of a non-commutative bundle, so a non-commutative principal bundle, which is just over a point. And even in that case, isomorphism classes is highly non-trivial. So we have a lot of stuff in this space. And so this kind of conclude my talk. And if for the interested listener, these are 3 references I recommend. And thanks for your attention.